It's a real pleasure to introduce Professor Peter Michor this morning, who is going to talk about soliton solution of the elastic metric on the basis of curves. And it's a joint work with all these people that you can see.
So good morning. Many thanks to the organizers for inviting me and giving me the possibility to talk here in this very interesting place and at this very interesting conference. This is the abstract, and the topic of my talk is solitons. So we managed to find solitons on a space of curves, so not on a group, and this was quite a surprise for us. And so I will start. What are solitons? So this is from Wikipedia, and there it says a soliton is a self-reinforcing solitary wave packet that maintains its shape while it propagates at a constant velocity. And
Sentence 2 is wrong.
Sentence
2 is wrong.
This is from Wikipedia. It's not.
Yeah,
It's wrong.
that defines the truth.
You cannot.
Solitons are caused. So solitons are not caused by cancellation of nonlinear and dispersive effects in the medium. So a single consensus definition is difficult, and here is the Wikipedia version. They are of permanent form, they are localized within a region, they can interact with other solitons and emerge from the collision unchanged except for a phase shift. The second is probably also wrong. So the solitons that I shall consider are solitons in Hamiltonian systems. And in principle, we are looking for solutions of an infinite-dimensional Hamiltonian system on a function space where the momenta are sums of delta distributions. And we will try to find solitons with this property. So let us look for soliton geodesics on diffeomorphism groups first. So this is just background information, and maybe my understanding is not completely correct, but Daryl will correct me. So right invariant Riemannian metrics on a diffeomorphism group. So M is a manifold, a compact manifold, or Rn, and diff C means diffeomorphisms with compact support, which is the most easy to understand. Compact support means the deviation from the identity is only within a compact region, and they are generated by an inner product on the Lie algebra of vector fields on M, and the inner product, this is given by an inner product on the Lie algebra, and this is written like an operator L applied to a vector field, taking an inner product with respect to a Riemannian metric on M that we need, and integrate it over the manifold. So here it's written for Rn, where L goes from vector fields with compact support to distributions, to the dual space. And the geodesic equation can be written very compactly in terms of the momentum, namely if we have a curve and we have its time derivative Vt, then this is a vector field along phi, and we can take this inner product here, and it's a linear functional on vector fields, and therefore it is in here, and this is just pushed forward by the solution from the initial momentum. So from this you can extract the whole geodesic equation, and one can ask whether generalized solutions u of t, this is d pi dt phi of t composed with phi of t inverse, So this is the right logarithmic derivative of the curve in the group, which now becomes a curve in the Lie algebra. So this is a time-dependent vector field, so that's the velocity field. We call this u of t, and one can ask whether such u of t exists such that their momenta p of t are distributions with finite support. The geodesic for such thing may exist only in some suitable Sobolev completion of the group. The momentum then is constant, and this means if we just put this on the other side, the upper star, the pullback becomes a push forward. So we see that the momentum is carried by the flow, and it stays a distribution with finite support if it was a distribution with finite support. So if we can find such a thing, it has very special properties. So the infinitesimal version, if we differentiate this equation here, it is just this equation, and here is just a Lie derivative along u of t of p of t. I mean, there are, of course, analytical problems behind that, because if u of t is only in some Sobolev class, so the Lie derivative must still make sense. And this is just the co-adjoint action on p of t of u of t. So you see here are only group things, and the metric disappeared completely. The metric is really hidden in the relation between p and u. So let us look for some examples, and we start with those that are easily understandable, namely for the Hunter-Saxton equation, and I take the diffeomorphisms of R with compact support, and I have to take a semi-direct product with R where the diffeomorphism group is the normal subgroup. Because if we don't do this, then the geodesic equation doesn't exist, which was quite a surprise. So we take those smooth functions on R whose derivative has compact support, which means it's constant near plus infinity and near minus infinity. And I can also require that near minus infinity it's 0. Then I look at the group of diffeomorphisms of the real line, which are of the form identity plus f, where f is in this space, and where the derivative of f is greater than -1, so that the whole thing is a diffeomorphism. Then we can use this right invariant metric, the H1, Sobolev H1 dot metric. So this is really a Pepo-Levi metric, because Pepo-Levi spaces were there before Sobolev spaces, and they were more general because they didn't start with the zero order thing, but Pepo-Levi objected fiercely to his name being attached to these spaces. There are some papers in the 50s which have Pepo-Levi spaces in the title, but Sobolev didn't object so fiercely, so these are called Sobolev spaces now. So this metric is just, you take two vector fields which are just functions and take their derivatives and the inner product of their derivatives, and then we integrate by part. We get this here, and this operator L, the inertia operator, is minus second derivative, so it's minus Laplacian. The geodesic equation is the Hunter-Saxton equation, and here you see it, phi sub t, time derivative of phi composed with phi inverse, so left logarithmic, right logarithmic derivative is u, and u sub t is of this form, and the induced geodesic distance is positive. The geodesic equation is locally well-posed, and the classical form of the Hunter-Saxton equation you get if you differentiate this with respect to x, and you get this thing here. Here some papers if you want to read up on that. So Jonathan Lennels did this on the diffeomorphism group of S1, but there you have to factor out S1. You have to factor out rotations. On R, this is taken care of by allowing constant shifts near plus infinity. So this has a very cute property, namely there is a square root velocity map or an R map. So you take this R map, you take these diffeomorphisms in this group, and you map it to its derivative, then the square root of the derivative, then minus 1, this is because we write identity and so on, identity plus f, and then twice, so that the scaling is correct. And this goes from this diffeomorphism group to smooth functions with compact support, and it has an inverse, and the inverse is this quadratic mapping here. So of course the values are always greater than minus 2 if you come from a diffeomorphism. So it has an inverse, and the theorem is if you pull back the flat L2 metric from this space to the diffeomorphism group, you get exactly this H1 dot metric. Therefore, this space is a flat space in the sense of Riemannian geometry, and you get explicit formulas for geodesics, because in this space with this fixed L2 metric with constant volume, it's easy to write geodesics. They are just straight lines, and you feed them in here and you get the geodesics. And, you can do nearly everything with this geodesics, and you see also, if we don't allow these shifts near plus infinity, if we just take the subgroup of diffeomorphisms which differ from the identity with compact support only, then the geodesic equation doesn't make sense, and these geodesics that we have in this larger group, they hit this submanifold exactly in 2 points, and they go either like that or like that. Geodesic distance is the same, and yeah. So what are the soliton-like solutions here? So the space of n solitons of order 0, so we look at momenta of the form delta distribution at point yi multiplied with a constant. So ya is in R2n. So we look at an initial soliton. The soliton P0 is inertia operator applied to U0. U0, that's the initial velocity, is minus U0 double prime, and this is this delta, so you have to integrate this up. So if we integrate it up, we have this, then U0 prime is a combination of Heaviside functions, where the Heaviside functions must have value 1/2. So the Gibbs phenomenon, you must take the Gibbs phenomenon, because otherwise the whole thing doesn't make sense. And U0 itself is just a linear combination of such functions, where D is 0 for negative numbers and is just x for positive numbers, so it is this function. Then you can compute a geodesic with this initial velocity U0, and you get this geodesic in completely explicit form, and its velocity field looks like that. Okay, so this was a very simple situation, but it was the situation that gave a lot of motivation to us looking for other soliton solutions. So this is a little more complicated. This is solitons on the universal Teichmüller space with the Weil-Petersen metric. So this is the diffeomorphism group of S1 modulo PSL2R, and maybe I can, yeah, I should not spend too much time, but I can explain it a little bit how this works. There is conformal welding. because we heard a talk on conformal methods for shapes, for planar shapes. So suppose we have a shape somewhere here, and we take the unit disk, so this is just S1, and let us assume that this shape has smooth boundary. Then we take the Riemann mapping, the interior Riemann mapping, and let's call this U minus for interior, which takes the interior to this, and the exterior mapping U plus, which takes the exterior of the disk to the exterior of this, and then we go U plus composed with U minus inverse, and this gives a smooth diffeomorphism on S1. And if we fix the exterior mapping by mapping infinity to infinity, then this mapping phi is unique up to a Möbius transformation on S1, and the Möbius transformations are in the PSL2R, and this is the diffeomorphism that you have. And if you take such a diffeomorphism, you can reconstruct the curve by taking the southern hemisphere, taking the northern hemisphere, and glue them together with phi. So you get a sphere, and you get a complex, so the sphere has a unique complex structure. So you take the unique biholomorphic mapping to the Riemann sphere, and in the standard Riemann sphere, the equator will become this thing here, up to Möbius transformations of the sphere, so up to shifts and scalings and whatever you can do with Möbius transformations. And then you look on diff S1 modulo PSL2R, that's a coadjoint orbit of the Virasoro group, and you look there on this the metric that you have there, and this is universal Teichmüller space, and there exist solitons, and these solitons are called teichons, like Daryl suggested 15 years ago. And here is an image of teichons, and here is this paper where this conformal welding approach was developed, and Kushnarev made many experiments with teichons. So the next kind of solitons is incompressible flow on diff Rn. And here I wrote H infinity, which is the intersection of all Sobolev spaces. It's smooth functions, but it's larger than the smooth functions of which decrease rapidly. And the metric that we look at is for epsilon to 0, and we write the metric as G epsilon at the identity of two vector fields is the integral over the inner product of the two vector fields, dx. So this is just the L2 metric. And then we have 1 over epsilon square divergence of V times divergence of V. So we punish deviation from being divergence free with a weight epsilon. And then we integrate by parts here, and we get the form that we discussed before, where now this L epsilon is identity minus 1 over epsilon square grad diff. Not diff grad, which is Laplace, but grad diff. This is not elliptic. Unfortunately, this grad diff has rank 1 if you do it. So we regularized it by putting a regularizing operator in front, 1 minus Laplace, with some constant which scales in the right way, to the power p to go up, and the p must higher than the Sobolev threshold of Rn. And so if epsilon goes to 0, this L converges to this L epsilon, and if epsilon goes to 0, this really converges on volume-preserving diffeomorphisms to the Euler flow of incompressible fluids. So for here, we have solitons. They were called vortons, and there was no objection by Darrell against the name vortons. So here you see
some alien in Star Trek that are called like that, or something.
I'm not a specialist in Star Trek. I have no television at home, so I see it very rarely. So you see, this is one vorton traveling here, and this is how R2 is deformed. If this vorton travels here, so this is really the momentum. And what happens with velocity? What happens with velocity is here this vorton travels, and the velocity goes along. A dipole comes along, and the flow goes around this dipole. And if the whole thing were in R3, you rotate it around, and you get a vortex ring. So you have a ring where the flow goes around this ring, and this travels along, and then one can, since these solitons here, they are really a finite-dimensional Hamiltonian system. If you fix the number of points, you can really play around a lot with numerical experiments, and you can see that vortons, if they go together, they start to spiral into each other or other things, and you can look in this paper for more information on that. So, solitons for the Kamasa-Holm equation and landmark space. So landmark space is a space of solitons, and this is very clearly but in a formal way spelled out in a paper by Darrell, Holm and Marston, momentum maps and measure valued solutions. So the Kamasa-Holm equation is the geodesic equation on either the group diff C of R with the full H1 metric for the dispersion-free version, or on the Virasoro group for the version with dispersion. And both versions admit solitons which are called picons. So landmark space is a space of n different points in Rn, pairwise differing points in Rn, where the LDMM method from the diffeomorphism group of Rm acts on these points and shifts them around. So you look at the diff-M orbit through these points, and you induce a metric on landmark space. But landmarks are exactly solitons for the diffeomorphism group with the LDDMM metric, where the metric is given by this kernel, which is the only input you need if you do LDDMM. You learned this in Laurent's talk. Diffeons. Oh yes, diffeons. And I read diffeons, yes. I read diffeons in this paper, but I forgot to write it down here. So KdV solitons are the most famous solitons. They have a different origin. They do not correspond directly to momenta, because there we have just the L2 metric, and the inertia operator is the identity. So it doesn't take a delta distribution. It's in inverse. It's not smoothing. It doesn't take a delta distribution and make something continuous out of it. But when preparing this talk, it came to me, maybe the KdV solitons can be approximated if we regularize the L2 metric with, like we did with the Whartons before, but I didn't have time to do the computations. Maybe it is done already. Daryl, do you know?
The KDV solitons are geodesics on differentials with respect to a central extension.
Yeah, yes, on the Virasoro group with a central extension, but it's the L2 metric, so the inertial operator is the identity, so it's not smoothing. But if you regularize it, put 1 minus eta square over p Laplacian to the power p in front, and then let go, then solitons exist, then you let go eta to 0, and probably these solitons would converge to the KDV solitons. That is what came to me when I prepared this talk, and maybe this was done by somebody. No? So that's a problem, and it could be done, and I will try tomorrow. Okay, note to self-check time. Perfect, because this is half time.
Oh, we have a break?
Huh?
Great.
No, it is just that my speed corresponds to the number of slides that I prepare.
Actually, you started 5 minutes late. So
Okay, so but we need also a little time for discussion. So this is now really what I want to talk about. That before was just related material in order to give you a survey of the landscape around. And I mean, for years I have tried to collect different definitions of solitons and to find a uniform picture of it. Sometimes it's possible in mathematics, sometimes not.
But just a comment here. The solitons you described so far don't have any dispersion, no linear dispersion. Okay, so the second sentence in the definition
Of Wikipedia.
yeah,
Yeah, you can correct it. If you go to Wikipedia, you can correct.
not for me.
Okay, so now we will look at the reparametrization invariant Riemannian metric on immersions from S1 to Rn or R2 on Rn, which is given in the following way: the Riemannian inner product with foot point an immersed curve C, of two vector fields along C. These are vector fields, mappings from S1 into Rn, which are along C, is just given as before, like an operator L, which now depends on C, applied to H, inner product with K, and here is integration with respect to arc length. And if this L is equivariant with respect to reparametrizations of S1, then the whole thing becomes invariant under reparametrization, and we look like that. And the geodesic equation for this, I mean, this has been worked out many times, and in terms of the momentum P is really C sub T of the velocity, LC, and this acts as a distribution via this inner product, and we take arc length measure so that it's really a distribution, that we don't need, we don't have any curve dependence anymore in the duality between functions and distributions anymore. And if we differentiate PT, then we get this expression here, yeah, where in fact this HC should again be LC. So the main result is the following. we take again this H1 dot metric. So the LC is again, we shall see in detail later. So if we take piecewise linear curves, then they are totally geodesic submanifold of the space of Lipschitz curves with the H1 dot metric. This is the first statement. And the second statement is geodesics in this finite-dimensional submanifold are solitons in the sense that their momenta are sums of delta distributions. Okay. Now, if I put my jacket away, you will not hear me anymore. Okay, so no, this doesn't work. This is really bad. It worked yesterday at home.
Did you move the file?
Hmm?
Did you move the file after it worked?
No, I didn't. It would be a pity if it doesn't work. It worked at home, but now it doesn't work anymore. Maybe because the resolution changed. There were so nice movies, not made by me, but by Philipp.
You can show it during the coffee break.
This also doesn't work. This is horrible.
You don't have them stored somewhere? The movies?
Hmm?
You don't have the movie somewhere in a folder? The original file.
You can click direct on the movie file to show it.
Yes, that would be an idea.
Yeah, this is worth having, I'm sure.
So, now I have to let's enlarge this. Where do I click now? Here.
Do these have all the same sign, or some of them are alternating sign, or what? The momenta, initial momenta. The signs.
The initial momenta. So the first thing is it's a sphere with 4 points. So a digitized sphere and 4 points, and we give it momenta like that. And this is the LDMM version, what LDMM does. So it stops here.
Gaussians.
Yes, with Gaussians. And the other one, so I should increase this. And you see, it goes through itself. It goes through itself. And this is...
No, it's bouncing, it's not going...
No, it's not bouncing. Look, the C2 is above, and then it was below, and then it was above again.
It seemed to be above all the time. Can you try again?
Can you go?
Now the C2 is down,
yeah.
yes, you saw. And it is clearer in the next one. And let me do it here. So you see this is a sphere digitized in 8 points, and then you give it momentum just pointing down and up with cosine of the angle. So this stays and here it goes, but of course the momentum is then transported to other points. So let's show this once again. This is quite beautiful, and this is a soliton movement in this space here. And this is really a geodesic. This is not a numerical approximation. This is really a geodesic in the space of Lipschitz curves with the right Riemannian metric. I will come to that later. Okay. So let's go here again.
So it conserves both energy and momentum, right?
Yes.
And the momentum, I mean, the energy is quadratic.
The energy is quadratic. So now I am describing this metric on the space of Lipschitz curves. So the Lipschitz curves, we write them as Sobolev or Pesov space W1 infinity. So it is once differentiable from S1 into RD, and the derivative is in L infinity. Yeah, this contains Lipschitz curves. So we have Lipschitz immersions. We will define them shortly. And then we have to factor out translations, which we call tra, because it's so funny. And I will describe first this metric, then the well-postedness of the geodesic equation, local well-postedness of the geodesic equation, and then we'll show that piecewise linear curves are totally geodesic. So the H1 dot metric. So I1 infinity and I1 infinity modulo translations are Banach manifolds. And the metric is just the L infinity metric on the curve itself and the L infinity metric on the derivative. And translations one can factor out, it stays a Banach manifold. And then we look at this metric here. So dSH is differentiation with respect to arc length. So it is 1 over C sub theta. H goes to H theta divided by the length of C sub theta. That is arc length differentiation. Then we have the length of the curve C, and we integrate with respect to arc length. And if we just differentiate with the parameter that is given, it looks like that. So we have twice in the denominator and once in the numerator, so one cancels. And this LC is here. So this is the metric. So we have explicit global charts. We have to prove that a curve, an immersed curve from here to here, and we look at this in L infinity, that this is C infinity. It is a smooth mapping. And this is somewhat involved, the proof of this. Now, the setting is the following. We look at W1 infinity mappings, which have center of gravity, and this is not with respect to arc length, is 0, and similarly for the immersions. And then we take those which are only in L infinity, and we take center of gravity with respect to the arc length on C. So the whole thing is now in the tangent space for a space C, and then we have arc length derivative and its inverse and so on, and we have to really understand arc length derivative and the inverse of the arc length derivative between these different spaces here. And we have this, so we really have to look at this in detail, and then we can prove that the geodesic equation exists, and it is given by this form here. And this form is a little unusual because we don't use differentiation by parts with respect to this ds here. I mean, in almost other cases one uses differentiation by parts as much as possible in order to get this inertia operator. If we do this here, we have to go to a Sobolev space of order 2, and this doesn't contain the Lipschitz curves anymore. So it is very essential to do this without integration by parts in order to have still Lipschitz curves in the whole thing. And this geodesic equation is locally well-posed, and the exponential map is a local diffeomorphism, and this was previously known only for k higher than 1, and the proof is the Ewing-Marsden proof. It is just a smooth vector field.
Is phi 0?
What is phi? Where is the phi 0?
Pi 0.
Pi 0.
Ah, pi 0 was a projection. So pi 1 is the L2 d theta orthogonal projection, and pi 0 is the L2 ds orthogonal projection, and it is these mappings here, and these are the injections, and this is just technicalities to take care of that the center of gravity is fixed at 0. I mean, one must be careful about this. Okay, and now we come to solitons. So it's clear that piecewise linear curves, they are Lipschitz curves. So they are really in there, and then we fix a grid. So we have 0 to 2 pi, and we choose a grid in the theta variable. Then we have these piecewise linear curves and piecewise linear immersions. And piecewise linear immersion is just one where two consecutive points are forbidden to come together. Points which have more distance, more step distance than one, they can, you saw already the movie, they can go through each other. So, we have to show that the piecewise linear curves are a totally geodesic submanifold of the manifold of all W1 infinity immersions from S1 into Rn. And we already know these are the solitons in this situation. And the geodesic equation on this finite-dimensional submanifold with a fixed grid, I mean, this is a finite-dimensional Hamiltonian system. And if we take Rn is R2, we have this R transform, we have even explicit solutions for these solitons, and we do this here. So here is the theorem. The piecewise linear immersions, and this is again Sobolev 1 infinity, modulo translations, it's a totally geodesic submanifold of all Lipschitz immersions modulo translations, and the geodesics in this submanifold are solitons. And we have to look at the geodesic equation that you saw before, and we have to see that if the curve and its velocity are piecewise linear, then also the acceleration is piecewise linear as well, and therefore this is really piecewise linear with the same subdivision, and therefore this is really a totally geodesic submanifold. And the velocity ct is piecewise linear if the momentum is a sum of delta distributions. You just write it out and you check it. I mean, the combinatorial formulas to do this goes over pages and pages, and it's not completely trivial, but to summarize it here is quite obvious. So these are the interactions between adjacent solitons under the H1 dot metric, and this is the interaction under the LDDMM metric, and I already showed you this movie because if I click here it doesn't come. So, and now I show you another movie, and it is this movie. Okay, so we have this movie here.
Yeah, but we saw the title.
And this is a geodesic. This is really a geodesic. It is not a numerical approximation. It was done by Philipp. He devoted, I think, quite some time to make this precise. And this is the movie. So this is really a geodesic. They are moving around because the center of gravity of the whole piece stays constant.
Next time, don't call it thank-you.mp4 because that's
yeah, you were not supposed to see this. It is just because of the change of resolution in the computer. This movie calling didn't work, and I am not computer savvy enough to.
And so that's the end of it.
Yeah, so there are.
Peter, this is absolutely gorgeous. That's so interesting. I have a question about the completeness of space of solutions if you start with a smooth distribution. If you start with a smooth distribution of the space of curves, you may go to the delta function piecewise linear curves, right? Which would mean that flow is not complete. Perfectly complete. But once you're on the piecewise linear curves, then it's an invariant submanifold. It doesn't go anywhere. However, in the U, and it says thank you with that circle, those are still piecewise linear.
Yeah.
If you start with smooth curves, do you develop the piecewise linear ones?
This is one of the open questions. We collected it yesterday with Martin's Bruveris. So Martins doesn't believe it, but I think the following happens. You start with a smooth curve, you put on it a soliton momentum, and you look how it develops. And I think it converges to a piecewise linear thing, eventually. Geodesic completeness is not to be expected because we have H1 dot metric, which is too low in order to get geodesic completeness. So what might happen, we might fall out of the space of Lipschitz immersions namely two consecutive points might come together, and then we don't have the derivative anymore there. But the form of this metric is so interesting that we never divide by this. So it might be that there is a geodesic completion and that we just go through these points. And but this is absolutely not yet done. And we also don't know geodesic completeness of any of these finite-dimensional Hamiltonian systems. So we don't know how long they exist. There might be the same problem here, and we have not yet investigated this.
Well, I think that you start with this smooth curve, with this H1 dot flow on the space of curves. It's quite possible you'll go to keep breaking up into more and more jumps in the derivative along the curve. So things will try to approach being piecewise linear everywhere, and will, you won't have a finite number of these jumps.
Yeah. So I think what you are trying to say is, and this was the motivation for the whole thing, that this gives a very precise way for numerics. So it's not an approximation; it is really a geodesic, the numerics. And but one should have estimates, error estimates, distance estimates, and this is not yet done. Also, I expected a question: how about going to higher dimensions? Who is asking that question?
I have another question, but answer that one quickly.
I have one more question before I forget. I hope I don't forget. But so the idea that is most attractive to me in this whole area of the diffeomorphic flow is the emergence of singularities. Okay, so and that you create them from a smooth flow.
Yeah.
And it may be, exactly because you allow for divergence, you can, I think, you can create these singularities from smooth initial conditions. And that the emergence of singularities is an entirely non-traditional way of thinking about PDEs.
So blow up. Infinite time.
It's not. There's no reason to be sad after you have the delta functions formed. There's no cause for regret. Let's now have dynamics among this whole different space.
Yeah.
So before you answer your question, I have a few further remarks. You forgot one example of solitons that was found by Daryl and I when we looked at metamorphosis, is that if you take metamorphosis with a norm, so image metamorphosis with a norm, a strong norm so Sobolev norm on the images, you get solitons and soliton solutions. And
but they are outside the space. They are not inside your Sobolev group anymore.
Well, they are.
They have lower Sobolev order.
It's not in the group. It's a space of images. So it's a metric of the space of images.
Okay.
And it turns out that this metric is also a metamorphosis metric, which is probably weaker than the one we considered with Daryl and Anna. And so the data term is. And the L2 is related to the L2 norm of the derivative of the arc length derivative of the curve. So there may be a connection there between these.
Yeah, I will take note of that and we will look at it.
So my question beside that was, if you want to go to, so not higher dimensions, but parametrization invariance, I believe that you still have a totally geodesic. So if you mod out parameterization,
Yeah.
I think it's
No, we kind of, for these piecewise linear things, it's completely trivial to mod out parameterizations. We just go to arc-length parameterization, which is...
What do you mean by that?
Yeah, that's a canonical parameterization for a piecewise linear.
Yeah, but you can change the number of if
the number of edges is fixed. It's fixed.
Yeah. So if you don't make it, and you have your curve, but you allow for non-zero momenta.
Yeah.
So still soliton solution, but non-zero momenta between the edges. Then you still stay in the in the same.
I mean, all these with fixed discretizations, they sit inside each other and as totally geodesic submanifold. So it is a quite nice thing. And maybe who wants to know about higher dimension surfaces? Or shall I not? So let me go back to this H1 dot metric. Where was the definition? Here. And you see that the problem is the following. The arc length derivative with respect to arc length corresponds to the covariant derivative. So if we have a surface, here should be a covariant derivative. It should be the covariant derivative with respect to the pullback of the metric on Rn to the manifold M that we have here. But if we have only Lipschitz mappings, or we can differentiate once, the differential of an immersion is just L infinity. It is not even continuous, so the pullback of the metric, I mean, we might force it to become continuous, but the continuous Riemannian metric has no covariant derivative. People in relativity have tried very hard with this cry and this singularity formations to make sense of this. So this is an obstacle. So we have to go too high with our Sobolev class so that we are above the Sobolev threshold, above the Sobolev inequality, so that we can make sense of this, and this would be the volume form with respect to the pullback of the Riemannian metric. And so those piecewise, the meshes, the triangulated surfaces, they are no longer contained in our space. So they are somewhere outside, and the whole beautiful setting doesn't work as it works with curves. Okay, thank you for asking that question.